All right, so we talk about improbable differential cryptanalysis. So let's apply it to CLEFIA. Of course, by not going into much technical detail, but show how it works. So before going into the attack, let's see how CLEFIA works. So CLEFIA was designed by Sony Corporation. I think it was around 2006 or 7 at Chess Conference. So it became an ISO standard for lightweight block ciphers in 2012, but this standard is still valid in 2023, so CLEFIA is still a ISO standard. So Sony uses it for digital rights management. CLE, a French word, means key in French. And block size is 128 bits. It supports 3 key lengths, as in the case of AES. And for different key lengths, it has different round numbers. So yes, let me see. Yes, it is in chess. FSC 2007. This is the, I think, the initial paper where they explained the CLEFIA. So for the 128-bit key, we have 18 rounds. And as far as I know, the best attack breaks 13 rounds. So as you can see, these parameters looks a little bit similar to AES, but the main difference is that CLEFIA is a face-stat cipher, not an SPN cipher. So the picture is simple. In DES-like ciphers, we had 2 lanes. Now we have 4 lanes because the block size is 128 bits. So every line here represents 32 bits. Okay. So this is what we call a generalized face-stat structure. So as you can see, we have some whitening keys initially and at the end. So here we have a simple round functions, F0 and F1, and I will show you how they work. But as you can see, the result is XORed and it goes like this. Okay. So let's look at F0 and F1. Actually, they're almost identical. So let me go back. We have 32 bits input for the F0. So that 32-bit input actually divided into 4 lines, right? So these are bytes. So this 32-bit is XORed with the round key, 32-bit again. Then these 8 bits actually is mapped to then S-box S0 and S1. So you have S-box outputs here. So you have 2 S-boxes with dimensions 8 by 8. And then you have a matrix multiplication M0. It looks very similar to actually AES, but without round shifts. So F0 and F1 is almost identical. Only difference is that instead of a matrix M0 here, you have a different matrix M1. And the order of the S boxes here, S0, S1, S0, S1, you have S1, S0, S1, S0. And these matrices are given like this. Okay, so they're chosen in a good way. So if we go back to main picture, you have F0 and F1 here. But they're almost identical. It takes 32-bit input and produces 32-bit output. And it consists of round key XOR, 4 parallel S boxes, then a matrix multiplication. Okay, so let's look at the impossible differentials and let's extend it to improbable differentials. So in literature, there was a 9-round impossible differential, actually 2 of them. Found by Suno et al. Here, recall that our input is 128 bits. So in this paper, they say that if we don't give any difference to the first 3 words, and for the last word, let's make a difference in the first byte and do not touch the other parts. So this is actually a truncated differential because I'm not saying what kind of difference I'm introducing to this byte. I'm just saying that there is a difference. So it can be 0001 or 111, anything. So actually you can have 2 to the 8 different possibilities for this. This is why this is a truncated differential. So they prove that actually using the miss in the middle technique, this input difference never goes to this one. Okay, so if you only give difference to this byte, you cannot observe after 9 rounds only the difference in this byte. Okay, this is the impossible difference. Of course, there's a kind of a symmetry in the cipher. So if you give the difference to this byte, then it also still works. Okay. So what I did was that, why don't we introduce 1 round high probability differential? So let's give difference to these 2 words But let's design it so that this one, after the F0 operation, cancels this one. So this becomes 0 here, and this one goes to the here. So let me go back to picture. But I'm trying to give difference to these 2 bytes, but I choose them in a very specific way. So with high probability, this one cancels this one after F0 operation with some probability. So they cancel each other, so 0 difference goes here, and this difference comes here. Okay? So idea is to choose these differences in a very clever way. Okay? So this way, as you can see, this is actually start of the 9-round impossible differential. So at the top of 9 round, I'm adding this one single round. So this way, I'm having a 10-round improbable differential, which means that this input difference after 1 round most probably goes to this, and this one never goes to this. So this way, I'm saying that this input difference with very high probability does not go to this one. This is how you obtain the improbable differential. So by looking at the DDT table, I chose those differences in a way that they cancel each other with probability 2 to the minus 5.87. So this is something you calculate using the DDT, okay? Since this is not a direct characteristic, but I'm considering all of the possible input and output cases in the DDT, and I choose the best case scenarios. So we put 1 additional round on the plain text side and 2 additional rounds on the ciphertext side of the 10-round improbable differentials to attack first 13 rounds of CLEFIA that captures these round keys. Okay, so as you can see, these are like 1, 2, 3, and 4 bytes. So attack is trying to capture the 32 bits of the round key. So from there, you will perform an exhaustive search to find the full key. Okay, so let me show you the whole picture. So recall that I started my improbable differential with this, right? So this one, this one will cancel this. This one goes here. And after 10 rounds, we say that it cannot be like this. This is your 10 round. So let's add 1 round to the top. So this goes here. 0 goes here. This one goes here. So since there is non-zero difference here and 0 difference here, they have to cancel each other. So there is something unknown difference here. So you add 2 more rounds to the bottom. So you just follow these and see what kind of stuff happens. So once you do it, you observe some 0 differences in some places, but non-zero differences in some places. So this means that in order to perform the attack, what I'm going to do is as follows. Gather as many plain text pairs as possible having this input difference. Okay? Then look at the ciphertext difference and only keep the ones that have this difference because that will be useful for me. Other pairs will not be helpful for me. So when I gather all of those pairs, what I do is as follows. In order to see that this difference is observed, I have to partially encrypt this 1 round, right? So in order to do it, I have to see that this difference cancels this one so that this becomes 0. In order to do it, I have to guess round key 1. Okay. Similarly, I need to guess a fifth stuff here. I don't need to guess round key 0 because this one goes here. And since there's 0 difference, it doesn't affect here and goes here. So I don't need to guess this key. This is the good thing. This is the way you perform actually less operations at the end. So in the literature, Suno's impossible differential attack actually was on 12 rounds. And it required this many data, this many time complexity, and this many memory blocks. So in our case, since we actually perform a, not an impossible differential attack, we introduce some probability. So our attack actually has some success probability. Not 100%, but close to it. But as you can see, I increased 1 round, but I ended up having more data and time complexity and so on. So for the other key lengths, we did the similar thing and improved this. Okay, so this just to show how you can extend an impossible differential attack to improbable differential attack and attack more rounds. So a very nice application. But then what happened is as follows. So now I told you obtain better 9-round impossible differentials. Here, you still give the input difference to this byte, but you cannot observe difference on these 2 bytes. So now, since I'm going to represent this as question marks or Y and Z here, I have more freedom to check. Okay, so this would actually reduce data complexity at the end. Moreover, they actually looked at the key schedule of CLEFIA and said that instead of capturing round keys, let's look at the key schedule and see the relation between round keys, because guessing a few bits or bytes of a round key might give you other bytes of the other round keys, so that you don't need to guess them twice. So these impossible and improbable differential attacks assume that the round keys are independent because we try to guess them. However, the key schedule of CLEFIA simply uses constant addition and bit swapping operation. Thus, some round keys have common bits. For example, for CLEFIA 128, round key 1 and round key 24 have 22 common bits. So if you know this one, and this is 32 bits, all you need to guess 10 bits actually, right? This actually makes things a lot faster, because in the key guessing part, since we are partially encrypting and decrypting, we need to guess these keys. We don't need to guess 64 bits here, right? We need to guess less. Okay. So by the way, I think I made a mistake when I was talking here, so I should correct it. I said that our aim was to capture these round keys, and I talk as if they are bytes, but they're actually 32-bit values, right? I said 32 bits in total, but actually all of the round keys are 32 bits, okay? So, since I don't need to guess all of these key bits, actually, you can improve your attack. So we did this, and as you can see, our improbable differential attack was this, with regard this many chosen plain text, this many reduced round encryptions, and so on. But we performed the same attack on 13 rounds by reducing the required time and data complexity. And moreover, by looking at the key schedule of 128-bit CLEFIA, we actually further reduce required data. Okay? And similarly, for larger key lengths, we obtain less data and time complexity attacks. So as far as I know, these are the best attacks so far. I mean, in the literature, some people introduce better attacks, then other people show that those attacks does not work, and so on. So to the best of my knowledge, these are still the best attacks. But still, it doesn't break the whole cipher, right? Because, for instance, for this key length, CLEFIA has 18 rounds. I can only break 13 rounds. So if it were close to 18, or if it were 18, then we should start worrying, right? And if it is used for digital rights management, like in the cases of PlayStation or that kind of stuff, so if you can obtain a practical attack, then you can capture the secret key in this hardware, right? Then you can, actually break the digital rights management. So this is why we need strong algorithms that is resistant to all of these attacks.